All right, I want to pick up where we left off. We were talking about carboxylic acids and carboxylic acid derivatives. We did some work when it came to talking about a little bit about the reactions that we already know that produce carboxylic acids. And we talked a little bit about the acid-base properties of acids, or sort of reviewing some of that Orgo 1 stuff. And then we got into naming. We named carboxylic acids, we named esters, and we named amides. I remember I said that in my course, I'm not really concerned about whether or not you can name acid chlorides or whether or not you can name anhydrides. But what we want to do now is start to move into the discussion of the reactivities of acid derivatives. We're going to start off with a discussion about acid chlorides and then move into anhydrides, then ultimately esters and amides. And the reason we're going to do it in that order is because that's the order of reactivity. All right, so if I take amides to esters to anhydrides to acid chlorides, this is the order of reactivity. Now, when we take a look at the order of reactivity, we can whoa, what just happened? Never seen that before. Just doesn't yeah, wow. Let me try, see if this is. Yeah, I have no idea how I made that happen. Anyway, this is the order of reactivity. Oh my goodness. Yeah, CHLORIDES, chlorides. Okay, there. A little bit of a limited embarrassment there. So here's the deal. If I take a look at acid chlorides, then we can talk about the inductive effects of the different electronegative elements that are attached to it. So we know that the oxygen is more electronegative than the carbon. We have shown the partially positive carbon of carbonyl groups for 2 semesters now. But what we're doing is we're adding a chlorine, and that's going to give me some additional inductive effects. And this ultimately makes the carbon more electrophilic than it was before. So that's compared to, say, an aldehyde or a ketone. When I look at resonance, I can think about a novel resonance structure. Now, of course, we know the resonance structure that involves just the movement of the double bond to the oxygen, but we can also show double bond forming between the chlorine and the carbon to make a positively charged chlorine and negatively charged oxygen. In a similar way, that we saw in electrophilic aromatic substitution, which was the reason why, even though chlorines are deactivators, there still were orthoparadirectors. The resonance effects in this case for the chlorine don't outweigh the inductive effects. And so this particular structure is not significant. If we look at the least reactive of the bunch, the amides, we can look at resonance structures for amides as well. And I think that at this point, you should know that this was one of the common resonance structures that we showed in that very first bit of organic chemistry that we learned. This is a major contributor to the structure. In fact, if we think about it in terms of how significant is the contributor, what we find is that amides are actually planar in their geometry. They're planar because there is a sufficient activation barrier for the rotation. Now, this is a single bond, and we would normally say that there's free rotation around this single bond, and that rotation would have a very small activation barrier. For amides, the rotation activation barrier is quite large. It's about 90 kilojoules per mole. And so what we see with amides is a planar geometry. And in fact, the fact that the doubly bound nitrogen to the carbon is such a major contributor to the amide bond is what plays essentially the entirety of the role in creating helical structures in proteins. And so we're not going to talk about it in this particular course, but if you get into a junior or senior level biochemistry course, you'll really dig a little bit deeper into protein structure, and you'll see that this particular resonance contributor is why alpha helices form in the first place. Okay. So for the carbonyl group, so in general, reactivity for carboxylic acid derivatives is similar to aldehydes and ketones and that's with respect to the fact that the carbonyl group is a carbonyl group. And so we talked about all of the different chemistry that happens with aldehydes and ketones. So all of that stuff applies to carboxylic acid derivatives as well. But there's one additional thing that's going on here. For a carboxylic acid derivative, I have some sort of heteroatom here, and the part of the deal is that this heteroatom can act as a leaving group. If I compare that to an aldehyde or a ketone, then I'm dealing with a hydrogen or an alkyl group, and these things cannot be leaving groups. So again, the chemistry for carboxylic acid derivatives is similar when it comes to the carbonyl group itself, but the addition of this heteroatom that can act as a leaving group brings up a bunch of other possibilities for chemistry that aldehydes and ketones can't do. And so that's what we're really going to focus our attention on, is that that particular type of chemistry, and that's called nucleophilic acyl substitution. All right. And what I'm going to show you is essentially the most general mechanism I can. Now, I'm going to show it to you with a negative nucleophile, but the nucleophile doesn't have to be negative. It can be neutral as well. Now we're showing that electronegative heteroatom acting as the leaving group. This wouldn't work with a hydrogen or an alkyl group. Okay, so what did we get? We've got nucleophilic attack, and we've got loss of a leaving group. All right, so this is the very generalized mechanism of nucleophilic acyl substitution. It's going to involve a nucleophilic attack and a loss of a leaving group, and it's always going to form a tetrahedral intermediate. But what might happen is we might need proton transfers depending on the conditions of the reaction. So let's take a look. Here's one example that fits really well with this basic generalized mechanism. If I have something like an acid chloride and I react it with methoxide, then I start out with a negatively charged reagent, in other words, basic conditions, and I form a basic intermediate. So in this case, I don't need any proton transfers because the conditions of the reactions start out basic, it's basic in the intermediate, and I form a negatively charged chloride ion in the process. Now, I don't need a proton transfer in this case, but what about if I use something under acidic conditions? Let's say that I start out with an ester and I do some sort of acid-catalyzed hydrolysis. If I were to just start out by using water as a nucleophile, then I would end up with a situation that is neutral overall, which is a little bit weird because we're in acidic conditions. So the conditions are positive. So having a neutral intermediate, while isn't necessarily terrible, it's not completely consistent. But what we really have a hard time with is we're creating in the intermediate a really basic oxide or a really basic, really negative charge on an oxygen. So this doesn't work out for us under these conditions. But what would work out is if I actually started with a proton transfer instead of a nucleophilic attack. So the first intermediate that I create is positively charged, and that's consistent with the conditions of the reaction. Then I can have my nucleophilic attack because the tetrahedral intermediate that's formed is also positively charged. Now, I'm doing hydrolysis, so I'm going to end up with a carboxylic acid. So I'm going to need additional proton transfers in order to continue on with the mechanism. I can't just take the OH and have my loss of a leaving group now. If I did that, I would have an OR minus leaving. An OR minus is very basic, so that's not consistent with the reaction either. So I'm going to need to do a proton transfer first. Now, I could do a proton transfer and protonate the OR group, but if I were to protonate the OR group, then I would end up with a species that has 2 positive charges, and that's highly unstable, so that's not going to work either. So the first proton transfer I need is the one that's going to neutralize the water that's already attached so that I can form something that's neutral. Now that I've formed this intermediate, I can now protonate the OR group, because doing so will create an intermediate that has a single positive charge. And if this thing were to leave, I would actually be pushing a neutral alcohol out, and that's going to be okay with the conditions of the reaction as well. And now I can do another proton transfer to form the neutral carboxylic acid. Now, this is the mechanism for hydrolysis of an ester. We're going to come back to it. It won't be today, but it'll be next week. So we'll see this mechanism again. But what I'm trying to illustrate at this point is that the conditions of the reaction definitely dictate whether or not you need proton transfers. So we started off with an acid chloride and basic conditions. That didn't need any proton transfers, but hydrolysis of an ester under acidic conditions certainly did need a proton transfer. In fact, it needed 1, 2, 3 proton transfers in the process to make it happen. But another way you can do hydrolysis of esters is under basic conditions. And now I can have nucleophilic attack be the first thing that happens in this case. Yes, I produce an negatively charged oxygen, but that's okay because that's consistent with the conditions of the reaction as it stands. Yes, the loss of the leaving group can happen immediately and push off a negatively charged oxide because that's also consistent with the conditions of the reaction. So I think I've mentioned having these reaction conditions being consistent in the past, but we really do talk about it a lot in this particular section. Well, I also then want to bring up a reminder from another chapter, the last one we did, with enamine and imine formation. Remember, they do the carbonyl groups react with ammonias, and this is going to be true with carboxylic acid derivatives as well. You remember that from the imine formation and enamine formation, it doesn't, even though it's under somewhat acidic conditions, it still starts with nucleophilic attack and not proton transfer. And the reason in this case is because the reagent itself is neutral. And my intermediate now is neutral as well. Okay. So this and this overall neutral. And this is overall neutral. So there's some other examples of this in this chapter as well. If we were doing it with water, this will also form a neutral intermediate, although it is a Zwitter ion in the sense that it's got a positive and a negative charge. And it'll also leave it there. All right, so what I want to do at this point is, I know that's kind of a hard break, especially considering one of the questions that was asked earlier today. I want to then go ahead and let's do this. Let's specifically draw out all the new reactions that I showed you in order to make sure that we have a specific understanding of what they are. So carboxylic acids under acidic conditions reacting with alcohols will produce esters. I can react an ester under acidic conditions with water, and I can reform the carboxylic acid. I can also take that ester and react it with an amine to form an amide. And amides themselves can be hydrolyzed as well. Back to carboxylic acids. Now, so let's talk about acid halides, specifically acid chlorides. Acid chlorides are the most reactive. But in order to get something that's the most reactive functional group to maybe use in synthesis, we have to form it first. We have to make it. SOCl2 looks like this. The mechanism as it's shown with Klein involves two nucleophilic attacks, or it involves a single nucleophilic attack, but sort of being instigated by the OH group. Forgot about this one. Okay, and now we can push off a chlorine. Want to make sure that we're following along correctly in this mechanism. Notice what I did here is I essentially rotated around this bond in the next structure. This double bond here goes from a double bond to a single bond. This double bond here, or this single bond, goes from a single bond to a double bond. And so I did rotate them so that the double bond that's getting formed points up, and the double bond that changes into a single bond points down. And the only reason I did that was for simplicity of drawing. So I just wanted to make sure everybody saw that. All right, so that Cl minus can come along. Oops. That Cl minus can come along. So what we have here at this point is a really good leaving group. And so if there is another chlorine ion or chloride ion in the solution, can react with this species catalytically and form a tetrahedral intermediate. So now what we're doing is we're into our standard nucleophilic acyl substitution mechanism. Now I'm reversing this just for simplicity of drawing. Now it's pointing down. And the last step reforms the chloride ion that we used up in the last step, or the first step, leaving me with SO2 gas and a chloride ion. And notice then I also created some HCl in this step here. And so the other products of the reaction are SO2 and HCl. So this is the formation of an acid chloride. Here is the reaction that you should know on the reaction board. So there's the formation of the acid chloride. Of course, I spent some time talking about this particular mechanism. I would expect that you know this mechanism as well. Okay, and so what we're going to do is we're going to start to get into the reactions of acid chlorides. So I think at this point in the semester, you should sort of be familiar with the flow of how this course works. We're going to, every time we introduce a functional group, even if it's sort of a derivative of the functional group, we talk about how to make it, the mechanism of how to make it, and then we talk about their reactions. And so now it's time to talk about the reactions of acid chlorides. And so one reaction is, of course, hydrolysis. I can reform the carboxylic acid if I have pyridine and water. Now, the water is essentially the operating reagent, but you'll see here in a second why we would use some pyridine. If I have water reacting with the acid chloride, what should I form? A positively charged or negatively charged or neutral intermediate? Well, notice that water is neutral, So I should form a neutral intermediate. And indeed, if I start off with a nucleophilic attack, that's what happens. All right. I can push off the chloride, leaving me with a protonated acid. With a final proton transfer, I'm forming a carboxylic acid. Now here's where the pyridine comes in. I've created HCl in the process, and this is a strong acid. And so we should know, especially from our discussion on aromatic compounds, that pyridine is an aromatic base, and it can go along and scavenge the HCl so it doesn't go off and do any other unwanted side reactions. And the reason that it's good at doing this is because pyridine in its acidic form is also aromatic. They're both aromatic, and that was what made pyridine a particularly interesting base. Okay, so there's going to be a variety of different reactions that use the same mechanism that I've just shown you. So I can take an acid chloride, and instead of reacting it with water, I can react it with an alcohol. I still need pyridine for the same reason I described before, because I'm going to create HCl as a byproduct. Now then, just be advised, I can show this from the perspective of the alcohol. So I can show you an alcohol reacting with a carboxylic acid to form an ester. So it's the same reaction. It's the same mechanism as from before. I'm just showing it from a different perspective. I'm showing it from the perspective of the alcohol. All right. So along the veins of those similar reactions would be the formation of amides from acid chlorides. Now remember that ammonia and amides are basic in themselves. So instead of pyridine, I just need two equivalents of the amide. And so I can form, or two equivalents of the amine. So I can form an amide, an amide that has no substitutions at the end position, or I can form a mono-substituted amide, or I can form a di-substituted amide. Again, these reactions proceed along the exact same mechanism that we discussed up here. The only difference is that instead of pyridine that's coming along and scavenging the acid that gets created, The amine does that scavenging for us, and that's why we need 2 equivalents of it. Just pause a beat real quick and see if there's any questions. All right. Probably not surprised that I can react an acid chloride with lithium aluminum hydride, and I can form an alcohol. On the second one, where did the nitrogen come from? So the question is asked, on the second one, where did the nitrogen come from? Well, I think it was here, right? RNH2. There it is. To produce RONRH. Okay, so the one before that was ammonia. There's the nitrogen to form ROONH2. Is that what you were asking about? Yep. But remember, in both of these situations, I need 2 equivalents. One to do the nucleophilic attack, and one to act as the scavenger for the acid that gets created. I think we know the mechanism of lithium aluminum hydride. And I think we even know how that applies to carboxylic acids. The exact same mechanism comes into play as it applies to carboxylic acid derivatives. But I want to just show it here again, just to remind folks. Remember that we can't isolate the intermediate aldehyde because lithium aluminum hydride is pretty strong stuff. And even if it's in excess, or if it's not in excess, you end up with a mess of products. So the most synthetically practical use of it is in excess to fully reduce the carbonyl group to an alcohol. Now there is a version of aluminum hydride that is analogous to the poisoned catalyst from our Orgo 1 days. If we wanted to produce an alkene from an alkyne, we couldn't just use H2 and platinum catalyst. We had to use a poisoned catalyst. It's the same idea here, but it's steric hindrance instead. What we do is, instead of lithium aluminum hydride, we use lithium oxyhydride of some variety. That's usually tertiary butoxide, I think, is the one that the book uses as an example. This will, by the same mechanism above, stop at the aldehyde. And ultimately, the reagent it reacts faster with the acid chloride, and not that it doesn't react with the aldehyde. It's just that it reacts much slower, and that means that you can isolate it. Now, let's see, acid chloride. Here's an oldie but a goodie. We started off the semester with Grignard reagent, and here we are almost at the end of the semester, and we're still using Grignard reagents. Just like Grignard reagent will act twice. Sorry, where would you use text butoxide and the one above? Oh, it's this R. I'm trying to identify what the R is. Yeah, no problem. I'm just, so what is this R group? The R group is some sort of big sterically hindered alkyl chain. I think the example in the textbook is tertiary butoxide. Does that make sense? Cool. All right, so I think you know that with a carboxylic acid, Grignard reacts twice. You know this mechanism. All the way back from the beginning of the semester. It's the exact same mechanism with an acid chloride. Nothing has changed here. So this is a perfect example of a reaction that, well, I guess could be new in the sense that I have never wrote down an acid chloride reacting with Grignard reagent. The results are exactly the same as long as we know that acid chlorides are derivatives of carboxylic acids, then we should already know how that works. Here's something new. This is called the Gilman reagent. I will say that Klein, it's a lithium dialkyl cuprate. RCU, it's a copper-based organometallic is the word for it. And what I will say is that Klein gives passing treatment to the Gilman reagent. If you were taking this course with a professor that used McMurray loves the Gilman reagent, and Gilman is everywhere in the McMurray book. But it does react with carboxylic acid halides. And what it does is it adds the R group one time from the organometallic compound. Now, keep in mind, Grignard is also an organometallic compound, but it adds twice. This organometallic compound only adds one time. All right. So that really concludes all of the reactions and mechanisms that involve acid halides. What we want to do now is talk about acid anhydrides. From the perspective of acetic acid, if we take acetic acid and we heat it up, not just a little bit, but a lot, then we can eliminate water and form acetic anhydride. This doesn't work for many other acids. It's really only for acetic acid. So in order to make other acid chlorides or acid anhydrides, what we do is we react an acid chloride with a nucleophile carboxylate salt. And that's what gets us a good acid anhydride. Okay. All right. So let's compare though. This and this these two things are both good leaving groups. They're similar as far as their ability to be stabilized. So if you remember from Organic Chemistry 1 and our discussion on acids and bases, we know that resonant stabilized carboxylates are pretty stable as well as highly electronegative atoms or halogens. They're also very stable, both of them stabilizing the negative charges very well. So they both have similar properties as far as being able to do act as leaving groups. And since they both can act similarly as leaving groups, then they do the similar type of chemistry when it comes to nucleophilic acyl substitution. So what did we learn? We learned maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 reactions for acid chlorides. We're going to have about the same number of reactions for acid anhydrides. So here's the difference. I mean, here's the thing though. They literally are the same reactions. They are literally the same reactions. So it's not that you have to know a bunch of new reactions. It's that they're all the same. And so what I'm going to do is I'm just going to rewrite them, the same reactions that we just covered, so you can see what I'm talking about. If I take acid anhydride and react it with alcohol, just like an acid chloride will form an ester, so will the acid anhydride. If I take an acid anhydride and I react it with ammonia, just like the chloride, I'll form amide. Of course, this same reaction is true with monosubstituted ammonia, or primary amines would probably be a better way to describe it. Oops. And it works the same way with secondary amines. Exact same products, almost identical reaction conditions. Same thing with lithium aluminum hydride. Same thing with sterically hindered aluminum hydride reagents. Same thing with Grignard. Same thing with Gilman reagent. Same thing with water. We've already discussed the reactions that create acid anhydrides. Okay, so actually what I'm going to do is just kind of recoup and say, look, that's 1, 2, 3, 4, 5, 6, 7, 8. That was 9, plus the reactions that form. That's at least 10. So there's definitely 20 new reactions. And so from that perspective, we almost learned 20 new mechanisms as well. But really, it's the same mechanism and it's the same set of reactions. So there's a question on the table. So what I want to do before I answer that question is leave it there for the day, and then we'll come back and we'll move on. So we did acid chlorides, and now we did acid anhydrides, and we'll move on to esters and amides after that.